Good morning, everyone, and thanks a lot for coming. Today, I'm going to present the work that we've done at the University of Toronto on the evaluation of file system reliability on top of solid-state drives. In the last 15 years, the storage landscape has changed. First, SSDs have started replacing hard disks as persistent storage units. However, their failure characteristics are different. For instance, partial failures associated with SSDs are an order of magnitude higher than those for hard disks, a trend that will likely get worse with QLC drives. Second, FTL has been shown to be more prone to bugs during power faults, mainly due to its high overall complexity. Finally, file systems have evolved significantly. ext3 has been replaced by ext4, while new file systems have been introduced, such as Btrfs and F2FS. These three file systems cover three different points in the design spectrum, ranging from journaling to copy on write to log structure approaches. In our study, we explore how file systems, the ability of file systems to detect and recover from partial drive errors. So, what do we currently know about this? The RM file systems paper studied 4 file systems that were common back in 2005. However, this study includes errors related to hard disks only and does not consider file system checkers. In our study, we focus on 3 modern file systems and explore their ability to detect and recover from errors, along with the ability of their file system checkers to resolve issues offline. In our study, we focus on local file systems deployed on top of a single SSD. And in our study, we ask the following questions. What happens if the underlying storage device starts misbehaving and generating errors? How can the file system deal with those errors? And what are the actual errors that can take place? So we begin our study by considering all the different faults that can take place within an SSD and map each fault to the corresponding manifestation at the file system level. For instance, while reading a block, an SSD may encounter an uncorrectable bit corruption, which will result in a read I/O error at the file system layer, since the corresponding data is no longer available. Second, an incomplete program operation within the SSD can manifest either as corruption or as a shorn write. Note that this particular fault is silent. The SSD itself cannot detect the error using its own internal mechanisms. A shorn write in particular denotes the case where a write issued by the file system is partially persisted within the SSD and can only occur after a power fault. So future reads after a shorn write has been persisted will only receive partially written data. Finally, dropped writes have several manifestations at the file system level. For instance, they can result in a write I/O error if the corresponding SSD cannot accommodate the request, or worse, the write request can be completely disregarded with the SSD never returning an error about it. We refer you to our paper in order to find all the different faults that we considered in our study. So, considering that the SSD itself cannot be modified, and also that we prefer not to modify the source code of file systems, then we had to come up with a different way to test the resiliency of file systems against the different SSD faults. An important observation that we made was that all these things look exactly the same at the block layer. And for this reason, we decided to emulate the fault's manifestation by injecting errors at the block layer. Specifically, we implemented our own device mapper module, which sits in between the file system and the block layer, and is capable of intercepting every single I/O request. In particular, the module can fail a single request and return an error to the upper layer. It can silently drop a request to the disk, or it can alter our block's contents online in order to emulate shorn writes and corruption. For every particular error that we inject, we study the file system's behavior in detail. Understanding the effect of an error depends on which part of the file system is affected. File systems employ different policies depending on the operation and the type of the affected block. For this reason, it is very important to identify and target specific data structures and fields within blocks. To achieve that, we use a combination of different techniques, which involve tracing of all I/O requests and offline file system tools such as DAM, in order to be able to inject different errors into targeted data structures and fields within blocks. Applications interact with the file system by issuing system calls. We consider different applications which pedantically follow POSIX semantics and call fsync to persist their data. In particular, each application focuses on a single operation, such as mkdir or create. During our experiments, we run an application and collect all the different blocks that this particular application accesses. So by using the IO trace, we can collect all the different blocks, and then what we do is that we repeat the execution by injecting a single error into each access block, targeting one block at a time. This approach gives us the ability to better isolate and characterize the file system's behavior and reaction to the corresponding injected error. So for each individual test case, we categorize the file system's detection and recovery policies by using all visible aspects such as logs and return codes, and also by comparing disk images. At the end of each test case, we also invoke the file system checker and observe if it was able to actually recover the file system. We have several recovery and detection levels, along with a few additional categories that pertain to file system checkers. For instance, error detection at the file system level can take place via error codes or by sanity checking the return block, while recovery can take place by retrying the operation or by propagating the error to the upper layer. We refer you to our paper in order to, for the complete taxonomy used in our study. In our experiments, we considered different applications, data structures, and modes, exploring over 7,000 test cases in total. This is a complete view of all our results. In the remainder of the presentation, we will focus on each file system in detail and present the most important findings for each one of them. But as a general observation, we would like to point out that in 16% of all these cases, the file system became completely unmountable or completely unrecoverable by the corresponding system checker. This is a 5,000-mile view of our results. As we observe, ext4's reliability has significantly improved compared to ext3. Btrfs excels at detecting I/O errors and corruption events, but the file system fails to recover in several cases. F2FS has the weakest detection and recovery against all the different errors that we emulate, despite the fact that it's actually a file system that's tailored for flash devices. So, beginning with ext4, we observe that ext4 is actually capable of detecting and recovering from a large range of false scenarios. Despite making little use of checksums, the file system is capable of dealing with corruption due to a very rich set of sanity checks. Due to the robustness of its system checker, several data structures can be reconstructed offline. Still, due to loss and shorn writes, sometimes the affected data structure cannot be recovered, resulting in data loss. Overall, we conclude that its reliability has significantly improved compared to ext3. I'm sorry. So, what about Btrfs? Btrfs is capable of consistently detecting all I/O errors as well as corruption events due to the usage of checksums. However, Btrfs disables metadata replication when the underlying device is an SSD, and that behavior is the default one. According to the official documentation, there are two main reasons for that. First, SSDs can internally deduplicate two identical logical blocks by remapping them to a single physical copy. However, this behavior would negate the purpose of increased redundancy and would waste file system space. Second, due to wear leveling techniques, an SSD controller may put data written together in a short time span into the same erase block. Therefore, if the erase block is lost due to an internal fault, both the primary metadata and its replica will be lost. This design choice causes severe reliability issues as the file system relies on metadata duplication to recover from errors. For instance, we will see how node-level checksums can result in data loss because of this particular design choice. So Btrfs organizes its data using a forest of trees, with each tree serving a particular purpose. Also, we observe that also the file system uses checksums in order to protect all its B-tree nodes. However, in case a single byte is corrupted, then a checksum mismatch will be triggered. And due to the fact that Btrfs has disabled metadata replication for SSDs, then the file system will end up discarding the entire node, suffering from data loss. In one particular test case that we ran into, the file system completely discarded 70 files and directories. Moving on, we observed that in some cases, Btrfs could not make use of the existing redundancy. For instance, Btrfs maintains two separate data structures for each directory. In case one of the two becomes corrupted, then the file system does not use the other for recovery, despite the fact that the information is right there. Finally, we observed several cases where the file system became completely unmountable and a few crashes while the file system tried to recover from errors. Even in those cases, invoking Btrfs, the file system checker, could not fully recover the error. Last but not least, we present our results for F2FS, keeping in mind that this is a file system that's tailored for flash devices. First of all, we observe that F2FS can successfully detect and appropriately propagate read I/O errors in most cases. However, the file system consistently fails to detect and recover from write I/O errors as injected by our framework. Also, the file system suffers from data loss due to lost and shorn writes. Regarding corruption, inodes and checkpoints are protected using checksums, but still, even for these data structures, recovery sometimes can be incomplete, resulting in data loss. Overall, corrupted data can have severe repercussions throughout the file system, as the remaining metadata structures are not protected using any form of redundancy, and sanity checks cannot detect every single issue. Finally, sometimes, and depending on the error, the corresponding file system checker can actually bring the file system to a consistent state. However, it cannot always restore all the affected files, and in general, it cannot deal with read I/O errors, as the system checker instantly terminates its execution with an assertion error. Based on our experiments and experience with all three file systems, we would like to highlight the need to verify the correctness of metadata when that particular metadata is being read from the underlying storage device, especially if the metadata is not protected by any form of redundancy. Second, we have observed that checksums can be a double-edged sword. On one hand, they actually increase detection, but on the other hand, coarse granularity checksums can lead to severe data loss. Finally, throughout our results, we observed that there are certain key data structures that can cause maximum recovery failures, especially when these data structures are affected by a silent error, such as corruption or dropped writes. We have made our tool and device mapper code online, and with that, I would like to end my presentation. Thank you very much for your time and attention, and I will be more than happy to answer your questions.
Thank you for a great talk. It was a bit frustrating to see that Btrfs has a specific default for SSDs, which makes it work worse. Do you think, in retrospect, that replication of the metadata would have helped in that case, in the case of Btrfs?
Okay, that's a very interesting question. So, at the creation of the file system, you can still provide the flag and say that, okay, enable metadata replication explicitly. But yes, in some cases, with that particular flag, then the file system would have been capable of detecting and recovering from some errors. But depending on the underlying SSD and the way that new blocks are written and placed into physical blocks, then there's still a chance that the file system cannot recover due to errors in the underlying device.
Thank you.
Hi, Rick Wheeler, Facebook. Two questions. First of all, great talk. I like the work. Have you thought about trying it for other file systems like XFS? And also, have you reached out to the kernel developers with some of your feedback?
Yes. So to answer, the second part of your question, yes, we have already submitted some bug reports, and we have already talked to the developers of the file systems. Some of the issues that we have reported have already been fixed, and we are currently working on 2 or 3 different fixes for some of the errors that we have encountered. Yes, regarding XFS, it's actually a very nice suggestion, and we are currently considering of expanding our study to that.
Thank you.
Thank you.
Peter Desnoyers, Northeastern. So, you know, in contrast to Btrfs, where that basically is something that could just be patched by changing a default in the makeFS program, you know, did you find, for F2FS, did you find that any of the issues are basically baked into the format? Or, you know, would it require on-disk format changes? Or is it higher level, you know, could code fixes change some of these things?
Yeah, so regarding Btrfs, at first we were a little bit surprised that the file system actually decided to turn off metadata duplication just because the underlying device is an SSD. But regarding F2FS, indeed, when we first began our study, inodes were not even protected using checksums, right? So in the process, they did they updated the definition of an inode and added checksums in order to protect them against corruption. So I would say that for some metadata structures, they're not protected at all against corruption. So I would say that even using, let's say, carefully implemented sanity checks, you cannot always detect every single issue. So I would suggest that, you know, for all the crucial metadata structures, they have to be protected again, you know, using some form of redundancy in order to basically be capable of recovering from several different errors.
Yeah, thank you.
Thank you.
Last question.
If we have a read layer below the file system, then what kind of errors can be shared by the read layer?
Can you please repeat the question, because I wasn't able to.
So basically in your experiment, you assume like there's a file system, then there's a single SSD, right? I'm saying like if we have a set of different SSDs and we build a read layer on top of the SSDs, then like what kind of errors can be protected by the read layer?
Yeah, so using multiple SSDs and using techniques like RAID, you can protect against different types of errors, but still, even using those techniques doesn't guarantee that every single error will be actually, you know, recovered, right? The file system has to perform its own checks and its own recovery policies to deal with any errors that can take place beneath it.
Thank you again.
Thank you very much.